So welcome to the 72nd Theoretical Physics Colloquium by Professor Jan Pawlowski from the University of Heidelberg in Germany. He got his PhD from Heidelberg University in 1994. After that, he had several postdoctoral positions at Friedrich Schiller University in Vienna and Dublin Institute for Advanced Studies. Before he received a research assistant and lecturer position at Friedrich Alexander University in Erlangen-Nuremberg. After that, he joined the Heidelberg University as a research group leader and as a professor since 2004 and 2014, respectively. He is currently a member of the cluster excellence at Heidelberg University called Structures. He has a wide spectrum of research interests that includes phase structure, thermodynamics, transport properties of QCD, renormalisation group methods, functional renormalisation group, Yang-Mills gauge theories, confinement and chiral symmetry breaking in QCD, quantum gravity, UV completion of standard model, ultra-cold gases, and many other things, magnetic and inverse magnetic catalysis, lattice gauge theory. I'm probably missing some other things. And today he will be talking about phase structure of QCD. And with that, I'll give the microphone to Jan.
Yeah, thank you very much, Igor, for this nice introduction. You didn't take my suggestion. I suggested to cut it short, and you even looked at my homepage with my research interest. Anyway, so today I would like to talk about the phase structure of QCD with functional methods. That maybe also explains the first question. The F stands for functional, and we even thought about calling it fun QCD, but that looked a bit not that serious, so we didn't do this. So here also the members of the collaboration. And you see also already the subject of interest, the phase structure of QCD. And as I think you all know, I mean, we know a lot about the phase structure at vanishing chemical potential because their lattice results are really up to the game. So you can trust the lattice here. But now if we go to finite chemical potential, the lattice phase is a sign problem. And we have also to look for other methods. I should say that I'm very much in favor of, getting our hands in particular about the critical point, which in the sketch of the phase diagram is a bit too high, I would say, in a combination of methods. I think we need all we can get in order to crunch down the systematic error we have at the moment. So as you see, this collaboration is located in Dalian in north of China, in Darmstadt, Heidelberg, and Gießen. And even though at the moment, we unfortunately are still working on our homepage. At the very end, there should be ready-to-use codes and also benchmark tests for our codes such that others can really participate in this endeavor. Okay, so here a bird's-eye view on my talk. I have to say, I think a bit about functional methods. I try to keep it relatively untechnical. I was already told that still a bit technical, so my apologies, but I think I have to tell you where our results come from, how you can trust them, or whether you can trust them at all. In the slides of the talk, which are now in the Dropbox and will be open to look at after the talk, there are loads of more technical slides and references which maybe give you also more information. So after this introduction on functional methods, I will start telling our results on the phase structure, and I give you already a sneak preview if you wish. That's our phase diagram of QCD, and there are different lines here I want to explain. And I will already say that this area here, which is mu t is larger than 4, we still fight with systematic errors. So that's just a suggestion. That's not a reliable result so far. But I try also to tell you how we want to crunch down the error. And then I also will talk about fluctuations of conserved charges. That's also our link to the experiment. And we hope also there to, from our functional methods, functional renormalization group approach, to get also these fluctuations of conserved charges in a larger area of the phase structure in order to use this also in combination with lattice results and predictions from experiments for prediction for the critical endpoint. Okay, let's come to functional methods. So the main method I'm using here is this functional renormalization group, which is a Wilsonian approach to physics. So we introduce a large infrared cutoff, which we call K, and we suppress all quantum fluctuations below this cutoff, which means in QCD, we are going to the asymptotically free area of the theory. And there, of course, we can take perturbative input or even classical input at the beginning. And then we just integrate out physics in momentum shells. And this integration in momentum shells is governed by the flow equation. So at the very end, we are interested in the free energy or the effective action, which is the generating function of all correlation functions. They are one particle irreducible, but that's just a technical, if you wish, term. So the free energy, if I take a momentum step, so I take a cutoff derivative of the free energy, the reaction is just a bunch of loops. And even though this looks like one loop diagrams, perturbative, these are full non-perturbative diagrams. So this object here, which is running around, is the full gluon two-point function with full momentum dependence and full field dependence. The same here, the second line here is a ghost loop that tells you already we have a gauge fixed approach, because these functional approaches are based on propagators, which then of course have to be defined in the first place. We have a Quark diagram, and then we have diagrams for effective degrees of freedom. And one of the things I try to convince you of, that this does not signal that we have an effective field theory approach, but we can incorporate them as an efficient bookkeeping device in our QCD approach. Okay. A very similar equation is the functional Dyson-Schwinger equation. I will also show you results with the functional with Dyson-Schwinger equations, and the comparison of these two results, results of these two methods, which you can see as results from different resummation schemes in QCD, give us yet another benchmark test. So one of the systematic error controls we have is that these are closed equations, which means I have not left out higher diagrams. This is a one loop exact equation, but one loop does not mean too much because it's one loop in full correlation functions. The same here for the Dyson-Schwinger equations. It's a two loop exact equation. So yet again, it's in full correlation functions. So you cannot solve such an equation in full glory. So you have to do approximations. However, if, for example, I just leave out this two loop diagram, let's say I'm saying it's small, then I can get my results with the rest and can insert this in this diagram here and make a self-consistency check. Keep in mind, if I then show that within this approximation, this diagram is small, it does not mean that I have a good approximation, but it's a self-consistent one. Okay, so the systematic error, to get our hands on the systematic error, is something we are very much interested in, and it's of course very difficult. Okay, so let's come to how does this really work? Of course, I don't want to give you the details here, but it's a set of diagrammatic equations for correlation functions. So I told you already that this is the gluon propagator. So what we need is an equation for the gluon propagator. So let's look at this in pure glue. So you see, yet again, this looks like standard diagrams you're used to in perturbation theory, but everything here is fully dressed. This, yet again, is a full gluon propagator. This is a ghost propagator. This is a full ghost gluon vertex, and so on and so on. And you see, for example, here for the gluon, the highest order diagram is a tadpole, which means in order to get our hands on the two-point function, we need the four-point function. Now, the four-point function has an own functional equation. I yet again give you some diagrams. These are not all, but all of these diagrams are one loop. So the highest diagram here will yet again be a tadpole, but a tadpole with a six-point function, and so on and so on. So you have a hierarchy of equations, loop equations for your correlation functions. And what we usually do is we truncate this hierarchy at some order. So for example, we could say we don't consider the 5-point function and fixed point function here and solve the system which is here. Now, you could ask why, for example, do we truncate here? Keep in mind, everything here is fully momentum dependent. This is a fully momentum dependent propagator, and this is a full vertex. This is a full 4-point function with 4 momenta going in with all the tensor structures you have in such an object. So this is an extremely long and difficult equation. And of course, I still have left out the meta loops. Right? There will be also loops coming from the 2 other diagrams. So, which means what I also need, obviously, is the Quark propagator. The Quark propagator couples to the gluons by the Quark-gluon vertex. I keep this Quark-gluon vertex here, and in the slides, there will be also some technical details. This object, as I said before, it's not an innocent object. It's a full 3-point function. It has 2 independent momenta, P1 and P2, and it has 8 tensor structures. So we have 8 dressings here, which have a momentum dependence P1 and P2. And in the best approximations we are considering, we are resolving the full Quark-gluon vertex, and we need at least, there are 3 dominant tensor structures. So we need at least to get our hands on the 3 dominant tensor structures to already in the vacuum to get close to QCD results. Then we have the 4-point function of the quarks, and you can imagine that there are resonances in this quark-antiquark scattering, which come from the hadronic degrees of freedoms in the infrared, and most prominently, of course, the pions. Right? So yet again, this object here, it's not just one vertex of 3 independent momenta. If you take already only the momentum-independent tensor structures in 2-flavor QCD, you have 10 tensor structures. In 3-flavor QCD, you have 26 tensor structures. And all of them, again, have dressings which depend on all momenta. Okay, so you see this system is becoming very quickly very elaborate. But the systematics we have here is you go in your vertex expansion from 2-point function to 3-point function, 4-point function, 5-point function, and so on and so on. Right? So this is the systematics we have. And of course, you can say, let's take everything into account up to all 4-point functions, and then go to the 5-point function and 6-point function and see whether anything changes. For example, for the propagator. That is the systematics we are after. But already taking all 4-point functions into account is at the moment beyond our technical abilities, just to tell you where we are. Okay, so now we have equations. For the quark propagator also, I showed you the gluon sector, now the quark sector, the quark-gluon vertex. Yet again, there are 1-loop diagrams. And keep in mind, these are again the full objects and the 4-point function. Now, if you are astute, you see already that there are some diagrams which maybe you can't place, because there's a dashed line and it's not the ghost. It's actually a hadronic degree of freedom, and it will be at the very end, it will be pion and sigma, so scalar and pseudoscalar channel. So what we are doing there is the following. We call this dynamical hadronization. We take the full 4-point function and write it as an S-channel or T-channel exchange. So it's a resonant channel plus rest. And keep in mind, the rest is still there, right? And then we define this exchange such that the rest is 0 specifically in this momentum channel. So it's a rewriting of the full 4-point function in a resonant channel and a rest. And then we take into account the resonant channel and the rest and go on. So it's really a rewriting. There's no double counting problem. It's a mathematically sound procedure, but of course at the very end, so what really is interesting are the approximations. Okay, it looks like Hubbard-Stratonovich. You can also call it a scale-dependent Hubbard-Stratonovich transformation, but it's an identity transformation. So that's very important here. Okay, so you look at the flows of these objects, and you get again flow equations for now this resonant propagation in the channel. the vertices, and so on and so on. So you see already, oh, sorry. This object here is a full 3-point function again, right? So it's not just some vertex with a point-like interaction. It is a momentum-dependent interaction, again, with 2 momenta. And this object here in the scalar pseudoscalar channel has 4 tensor structures, which essentially you can translate into the 4 components of the beta-Salpeter wave function. Okay, but the important thing is it's an exact rewriting of the original for Quark vertex in QCD. Okay, so you can actually do this game not only for mesons, you can do it for diquarks, baryons. That's also something important. You may say, why diquarks? It's not an asymptotic state. Everything we have here in these diagrams are off-shell objects. So a diquark makes sense to introduce if a diquark is resonant. And we know, for example, if you look at hadron formation or proton-neutron formation in the vacuum, that the scattering of a diquark with a quark into the baryon is the dominating process. Okay, so I'm not saying here that the diquark is an asymptotic state. I'm saying that it might be a resonant off-shell degree of freedom. Okay, so now in the vacuum we have pushed this very far. We just take the fundamental parameters of QCD, we put it in at a large momentum scale, usually something like 40 to 100 MeV. For precision, actually, we also went to 1000 GeV, not MeV, GeV, so 100 GeV. And then we put in the fundamental parameters and crank our machinery, and our results match those you get in gauge fixed lattice QCD for these correlation functions. We also can compute something, I mean, for example, the chiral condensate, which I also will use later as an order parameter for confinement, and it's in quantitative agreement with the lattice results. Okay, the approximation in the vacuum we have pushed it to at the moment is what is put down here. I will not explain in detail what you see here. I can only say that all the correlation functions which you have here, we put also back into our diagrams. So it's a self-consistent system we are solving. Everything we extract from the flow, we also put back into the flow. That will be, important later when I come to the consistency of what we are doing at finite chemical potential. Okay, so if you solve this system self-consistently, which means all the correlation functions you compute, you also feed back. If you are at finite chemical potential, it defines you an analytic function. If you do approximations such that you do not feed everything back you see here, then you will have problems. But if you do this approximation defines you an analytic function. So I will come back to this later. And yes, we are aiming at apparent convergence, but I hope I made it clear, getting apparent convergence in this systematic expansion scheme is extremely difficult, and we are not close to something like this, in particular at the moment at finite chemical potential and temperature. Okay, so that's the scheme we have. Of course, at finite temperature and chemical potential, we have to invoke further approximations. They are detailed in the slides in the Dropbox. I didn't want to go through it because maybe you would even doze away if I start now to explain what additional approximations we are doing. So I'm not hiding them, they are in the Dropbox. Okay, and if you're asking later in the talks, the slides are there so I can resurrect them. Okay, so we do additional approximations. Basically what we are doing is that we can write the flow equations and also Dyson-Schwinger equation in an expansion about the vacuum results. And then the only thing we have to compute are the thermal and density contributions. And if we do additional approximations there, in most cases, that is still okay, right? At the very end, of course, we want to solve the full system in full glory in the best approximation. But I mean, as I said, this is technically very difficult. And keep also in mind, I told you already that in the vacuum, the quark-gluon vertex has 8 tensor structures. If you go to finite density and temperature, the heat bath singles out the rest frame. So you get additional tensor structures, and this blows up the system enormously. So now here, our results. This is benchmark in the vacuum. What you see here is the 2-flavor gluon propagator and the 2+1 flavor gluon propagator, and the points are lattice results. So we are bang on the lattice results. In the ultraviolet, this leveling off of the lattice result is just a sign that they are not continuum extrapolated. They are actually plotted over the lattice momenta, so there's a sign in here. So this is just the perturbative result here, and the lattice levels off, so it's not our problem. It's also not the lattice problem. It's precisely understood what is going on here. But don't look at this and saying, oh, I mean, we deviate from the lattice. No, we don't. So here, yeah.
Quick question. Any fitting parameters when comparing with the lattice?
No. We have, if you wish, fitting parameters in Young-Mills because there's no scale, right? And then, of course, you have to say what the momentum scale is. And you could, for example, I mean, in let's say old times, it was a string tension. Now, usually it's the summer scale. Of course, if you look at gauge fixed correlation functions, you can just take the peak position, right? Which, as you see, is roughly at 1 GeV, and this is linked to the mass gap in QCD. So maybe I should also say I'm not really showing you the propagator, I'm showing you the so-called dressing function. So it's the momentum square times the propagator. So classically, this would be 1. So this decay in the ultraviolet is the logarithmic suppression you have due to the 1-2 loop anomalous dimensions. And we can also see how we run into this. And this going to 0 here just means you have a mass gap. So the physical mass gap in QCD in our approach, this is now QCD in the Landau gauge, is reflected in the mass gap of the gluon propagator. And we can also show, and we have done this, that if you want to have confinement, you need this mass gap. It's in one-to-one correspondence, and also the size and position of this mass gap then tells you about the phase transition temperature of the confinement-deconfinement phase transition. So the other things you see here are now additional curves, and they are at different temperatures. And we already took comparisons of Dyson-Schwinger results here from the paper with Fei Gao. So in 2020, in 2000, well, it's actually both 2020, the papers, and a functional renormalization group result with Weiji Fu, now Dalian, and Fabian Rennecke. He was in Brookhaven, now is in Gießen, from 2019. And the results match very nicely, and you can also compare them with 2+1 flavor results at finite temperature. There are not that many lattice results, unfortunately, for gauge fixed correlation functions at finite temperature because it's statistically very expensive, and not that many people on the lattice are doing this. Okay, there are of course more.
But in the future also here, in the future, more data come back to 3+1 here.
There's also a 2+1+1 data, right? And we are always begging the lattice people who are doing this to produce more data. And of course, we are in particular also interested in higher correlation functions. But you can imagine that then the statistical problem is really, I mean, increasing a lot. And then you need really, it's also so that not all configurations are well suited for an additional gauge fixing, right? So stout configurations.
Thank you.
Yeah. Okay. So I flash also some other results and more literature you find on the slides. So of course, we're not the only ones doing this. And now here, I mean, a very relevant parameter for computing the chiral condensate is the Quark mass function. And yet again, you see in comparison to the lattice results at 0 temperature. And then if you go to finite temperature, if you wish, just the mass, which, I mean, the size of the mass here comes from chiral spontaneous symmetry breaking, of course, melts down. Okay, so now we come to observables, and that's the observables which we also use to compute the phase boundary, and that's a chiral condensate. I'm saying a chiral condensate because there are different ones. You see definitions here. You can take the renormalized condensate, where you just take the chiral condensate and you subtract the vacuum value, and that then means you don't have to think about renormalization. In our case, because we have this dynamical harmonization, we immediately get a renormalized condensate. If you're interested in the details, you have to look at this paper with Wei-Chi Fu and Fabian Rennecke. It's essentially the expectation value of the scalar channel, which is just the Q bar Q, obviously, right? There's also, and you see, yet again, this is now at zero chemical potential, and we are bang on the lattice data. And there's no parameter going in. This is just taking what I said before in the vacuum. We take the physical parameters, the fundamental parameters of QCD, we compute, and that is what comes out. Right?
It is a little bit a question. So there is a temperature, high temperatures on the right-hand side, right?
Yes.
And your condensate is large and it is zero on the left. This
yes,
is because you subtract vacuum.
No, because it's renormalized. So what we subtract is the vacuum condensate. So if we go to temperature 0, this object is 0, right? So it's the temperature condensate minus the one at 0 temperature. So that's an object which goes to 0 at small temperatures and which goes, of course, to a constant at large temperatures. Okay, that's why it's so counterintuitive. However, if you want to see something which looks as you're used to, here is the so-called reduced condensate, which essentially is the light quark condensate minus a ratio of the masses times the strange condensate. It's exactly as you're used to. It goes to a constant. We have normalized it to 1 in the infrared at 0 temperature, and then it decays to 0. And we have also tested different differences of light and strange quark masses. And for the physical one, it's bang on the lattice results again. And if you go to different masses, of course, there's a small deviation for large temperatures where you see the current quark masses. Okay, so at 0 chemical potential, our results, and I will show you also later results for fluctuation observables. The results for fluctuation observables are not in QCD. They are in something which we call a QCD assisted model. I will explain what this is, are just fully compatible with the respective lattice results. And now keep in mind what I said. If we have a self-consistent approximation scheme, so everything we compute, we feed back in the equations, this defines an analytic function in the chemical potential. So if we have in our approach agreement with the lattice at 0 chemical potential, that's where the lattice computes. So if you do reweighting, you're still essentially computing at 0 chemical potential. Our approach defines an analytic extension of this, which is compatible with QCD. And that singles it out in comparison to other, let's say, extensions of 0 chemical potential results to finite chemical potential. Because we have QCD dynamics in, we may not have the full QCD dynamics in, I will come to this, but we have QCD dynamics in. It's not guessing an extension, resumming, we just compute it. And in my opinion, this is an advantage of the current approach. Okay, so this is now our result. You see a lot of data points. So most of the data points you see here are freeze-out data points from different collaborations. You see the lattice results. I mean, the green one for the Wuppertal Budapest and the brown one for the hot QCD. So of course, if you go to larger chemical potential, mu b over t is 2, they start seeing a larger statistical error. And the dashed lines, the black dashed line and the blue dashed line, these are now functional results. The blue is with a functional renormalization group. That's the approach I explained a bit. And the black one is with Dyson-Schwinger equations, where, however, the vacuum correlation functions have been taken from functional renormalization group results. That's also something which is very nice in functional methods. If you see a correlation function and you don't want to compute it, or you have a reliable result for that from other methods, you can just use it. Right? So it's a very flexible tool. Okay, so you see these lines are just essentially on top of each other. And the critical endpoint is the prediction, if you wish, for the critical endpoint is very close. So it's not really a prediction. I will now explain what these lines are, right? But at the moment, I just want to emphasize that the phase boundary is very close. So now I come to consistency checks. If I can move the slide. So first, one can look at the curvature of the phase boundary, and it's compatible with the respective lattice results. Now, I already put in the reliability region. So where it's red, in my opinion, our results are not yet reliable. I will explain this. While in the white region, I think our results are reliable, and I want to explain this a bit. Okay, so how do we check reliability? So as I said, we are leaving out higher correlation functions, and we are leaving out channels in higher order interactions. However, we can monitor their size, either by feeding back our results or by respective computations, which are ordered a bit differently, but specifically concentrate on the correlation functions we have left out. I also said that our systematic expansion schemes is we are leaving out higher order vertices, and you can ask yourself, when is a higher order vertex important? And of course, if you're coupling, and I'm not talking about the strength of the coupling, it's really the strength of the vertex. So if the strength of the vertex is becoming big, then of course you cannot just stop your systematic expansion. And of course, if you have resonant interactions, you have to take this into account, and you have to also consider that there may be multi-scatterings of resonant interaction channels, which of course you have in chiral perturbation theory. There you look at the, I mean, in our language is you look at the most prominent resonant, which is the pion. It's the lightest resonance in QCD, and you expand in pion interactions. Right? In our case, we would look at the 4 Fermi interaction. We would see this resonant pion channel. We would bosonize it and consider higher order scatterings of this resonant channel. Right? And then we monitor the rest of the 4 Fermi interactions and look whether another channel becomes resonant. This has been done in this nice paper here by Jens Braun and collaborators, where they took a Vierz-complete 4 Fermi interaction into account in QCD and scanned the importance. That's now measured in terms of the chemical potential. And what you can see here, you have these 10 channels, which I talked about to flavor computation, and the scalar pseudoscalar channel, so which is related to the condensate Q bar Q, is the dominant one. Keep also in mind that it's not really the size. Of course, the size tells you something, but it's the question, if you drop now one of these channels in your flows or Dyson-Schwinger equations, is anything changing? And what comes out is, if you drop the rest of these channels here, nothing is changing, right? So this object, you see already it's very dominant, but it's even more dominant than it looks like, because if you drop the rest, nothing's changing. However, at a certain chemical potential, the thing changes. So the scalar pseudoscalar interaction essentially goes to 0, and another one is just getting prominent, which is a diquark channel. Keep in mind, it's very dangerous here to think in terms of hadron resonances. This is a Vierz-complete basis, but what is a pion and what is a diquark depends a bit on how you redistribute your channels. It's not I mean, Jens and collaborators, they use the specific basis. You can use another one. However, what is just clear is there's one dominant channel for small chemical potentials, and there's another dominant channel for large chemical potentials. Unfortunately, they used a notation and scale setting, which is very difficult to translate. You see a 2 here. This is not, if you wish, mu b over 2 here. If you translate this in our setup, it would just, this transition point here would be here. Okay? But of course, you have to take into account that even earlier, I mean, mixing of channels starts. So if we make a conservative estimate, this investigation tells us, please only trust a one-channel approach up to mu b over t is 4. Now, in the Dyson-Schwinger approach, you can do similar things. You can look at the effects of baryons on the phase structure. So you take in your quark gluon interaction, you take a baryon resonance into account and look whether what changes if you take it into account or not, and the effects are minimal. Keep in mind, that's now a statement yet again for small chemical potential. It does not mean the baryon does not play a role for large chemical potential, but for small one, it does not. You can do the same for mesons. It's a very recent computation of Christian Fischer and a PhD student of his just 3 months ago. And you see the same. Yet again, it just means that for smaller chemical potentials, this does not play a role. Now, what you...
a question. Somewhere around 150 on this plot on the right, yes? We know that resonance gas start dominating by baryons.
Yes, that's
so
something.
This statement must be violated somewhere.
No. Wait a second. I left out this. It's again in the slides, and I can resurrect it at the end of the talk. One has to be very careful. I'm always told, how can this work? I mean, you're not taking into account 200 or more resonances, which we know the hadron resonance gas needs for getting, for example, the pressure right.
Correct.
Right? How do you get this from a one-loop fermionic contribution? If you see, I mean, we get it from essentially, so the matter pressure we get from the quark loop, or if you wish, if you make this dynamical hadronization, also from the, meson loop. Now, what the hadron resonance gas does is it makes essentially like a Katkovsky cut through the diagram and puts in a 1 in asymptotic states. And this object, you can even in perturbation theory prove this, is converging extremely slowly. While if you put in plane waves, which is what you do in a loop, it's converging extremely quickly. So these are 2 complementary pictures. So I'm not saying, oh, you should not use the hadron resonance gas. To the contrary, I like it a lot. But for this specific question, it converges not that fast, while a loop representation converges quickly. And if you don't believe my words, try to do this at one loop. And you can convince yourself.
So you're saying you don't need any baryons at all. You have quark loops.
No, I'm not saying this. I'm not saying this. The hadron resonance gas uses the asymptotic states of baryons, whereas everything we have here, and I try to be very specific here, are
virtual states.
Degrees of freedom, which are expanded in momentum modes. So this has advantages and disadvantages, right? But the advantage here is, I mean, for thermodynamic quantities, we definitely don't need the baryons. We have actually, I mean, this paper I flashed before with Kenji Fukushima and Niels Strothoff on the hadronization. I mean, Niels, of course, did most of the technical work, and we went up to a quark 12-point function in order to have a quark representation of the scattering of baryons. And we hadronized the baryon, so we had a baryon degree of freedom and looked for its importance in these loops. And it was completely unimportant. And yet again, don't misunderstand me. It does not mean that you don't need the baryon resonance to do a baryon hadron gas computation, but as an off-shell degree of freedom for the specific.
So you don't need additional auxiliary barrier.
Well, if you wish, let's look at the baryon contribution to meson, right? You have a baryon loop which has a baryon and an antibaryon. If you go with the baryon on shell, you are with the antibaryon very much off shell. And that is what suppresses usually. So if you dial the chemical potential, that is what usually suppresses these off-shell contributions to these loops, which of course is good for us, but we are not trusting it. I mean, we are checking it. And in this specific case, for the scattering of 12 quarks, and you can imagine this is a hell of a work.
Mm-hmm.
You have diagrams, right, where you have these 4 Fermi interactions and quark-gluon interactions, and a lot of them, and they have A tensor structures and more, right? And we were completely frustrated because the effect was nothing, which of course also comes from the fact that this is a Euclidean computation.
Mm-hmm.
So if you go to the
I got it. Yes.
You will pick up the resonances one by one. Okay. Now, but the lesson to learn from what Jens and collaborators did, is we have to up our game in this area here to a Firth-complete computation, which is costly. The other lesson to learn here is there is this red dashed area. And what we have seen here in the computation with Fabian Rennecke and Weijie Fu is that the pion dispersions got a minimum at a non-vanishing spatial momentum, which if you translate it into space-time means you have some spatial structure. So I call it in quotation mark inhomogeneous phase. We don't know what it is. It simply means there's some spatial structure. And of course, if you want to get your hands on this area here, you have to take this into account, which means maybe you have to use a non-trivial background. You certainly have to investigate this closer. Okay, that's.
So is this minimum reaches 0 or not?
Sorry?
If the dispersion curve simply have a minimum and then go up, and the minimum doesn't reach 0.
No, it does not reach.
It doesn't. So it doesn't mean it is a crystal.
No, I'm not saying, this is why I said quotation mark. But look, we see a non-trivial structure, and I want to be careful. If I see this, we have to take this into account.
We know liquid helium have that, and it is still homogeneous, right?
This is why there are the quotation marks. Okay. However, nevertheless, we should take into account a non-trivial background, which means we have to work more. And if you look at the intersection of this hash area, the hash area is where we have this non-trivial dispersion, and the condensate is relatively big. Because if you are just have this, we have this also in this area here, it simply means that the momentum structure of this exchange channel, which is completely irrelevant here, is non-trivial. But if you have a condensate, you have to be careful. So don't get me wrong, Ed. I'm not saying that there is an inhomogeneous phase or whatever. I'm just saying in this phase, we have to up our game. Okay. And if you look at the intersection of this hash area with the phase structure line, it's yet again at mu b over t is 4. Okay. So we have no indication whatsoever that anything is going wrong in this area here. We have indications that at least our approximation we have at the moment is not trustworthy for larger chemical potentials. Okay, so that is what led us to this line here. So below this line, the approximation is, in my opinion, reliable, which means we don't see any sign that something is going wrong. Above, we see that we have to better our games for better our approximations for making a prediction, which means that this is an estimate of our computation into an area where we don't trust the reliability of our results. So be aware of this. So that's not a prediction for the critical endpoint. It's just an estimate, right? So, which means if I take everything together, there is an estimate for the critical endpoint. in this area, which is a relatively large chemical potential, which means a relatively small scattering energy, if you translate this. Okay. However, we are at the moment working frantically on ticking off all the different things I have said we have to better. So let's stay tuned. Okay, so for the rest of the time, I will come to fluctuations of conserved charges, and I change now my approach a bit. So keep in mind that what I have said before is the best we can do in functional methods if we want to do QCD. Now I'm going to something we at the very end will call a QCD-assisted low energy effective theory. The first thing I would like to tell you or convince you of is I called this on the unreasonable effectiveness of low energy effective theory. I also like the movie a lot, if people catch the reference. And that is that if we monitor couplings of the different fields and low energy effective degrees of freedom we have put in by dynamical harmonization, there is a sequential decoupling. So what I show here is as a function of the cutoff scale. So keep in mind, we are integrating out momentum modes. So that's our flow equation. And now I show you couplings. The black one here is the coupling of the light quarks onto the gluon. So it's the coupling strength of, so here it's perturbation theory, it peaks. But then, so if you wish, it's an interaction coupling where two quark currents are related by a gluon exchange, because we have a diagrammatic language. And then the gapping of the gluon just leads to this decay here. And keep in mind, this is a doubly logarithmic plot. So if you see something very sharp, it's not, we don't have a kink here, but things happen very quickly. You see, I mean, here's logarithmic plot, right? So what we have is, of course, this, the quark-gluon coupling is dominating a long time, right? So up to 1 GeV, that's now really physical unit. So that's in 2+1 flavor QCD with physical quarks. The quark-gluon dynamics is the dominant one. And then the pion and sigma, so the dynamics of the resonant sigma pion channel, scalar pseudoscalar channel, is taking over. Of course, at some point, we see that the pions are nearly massless, while the scalar channel is gapped, and also the scalar channel decays. And at the very end, you are just left with pion dynamics. So this area here is chiral perturbation theory. So if you wish, what we see here is the dynamical emergence of chiral perturbation theory from QCD. Okay? But of course, now you not only have the very low energy dynamics of QCD, but also in between, you see that from this point on, so essentially below 1 GeV, the gluon dynamics is not relevant anymore. You still have non-trivial glue potentials, in particular at finite temperature and density, but the off-shell dynamics, now we come again to Ed's question, the off-shell dynamics is decoupling, okay? So which means that your full QCD theory is in this area here, you can describe as, I called it a direct sum. So now in this regime here, you have the dynamics of quarks and mesons, while the dynamics of the glue sector has decoupled. Now you can say, well, the ghost, if you know about it, is massless, but the massless ghost only couples to the rest via the gluon, and the gluon is the most gapped particle here. And that is what you have now here. You have a dynamical emergence of low energy effective theories. And I like this a lot because it tells you that, I mean, there's a systematic way to upgrade low energy effective theories towards full QCD by using input from the flow of correlation functions in QCD, which means you can do simpler computations, but still in the background, you have input from QCD. Okay, So that is now what we call QCD assisted low energy effective models. So it's like having a NGL model or Quark-Meson model or Polyakov loop enhanced, because you still have the potential of the Polyakov loop lingering around here. So QCD effective models where the ultraviolet couplings and vertices of these models are determined by QCD. And if you really go for it, you would not have point-like couplings then, but distribution functions. Right? You would have an NGL model which has not a point-like coupling, but has a four Fermi interaction, which you get from integrating out Quark-Lewin degrees of freedom in QCD. And we can provide this input, right? Okay, so now we take this. What we did is we took this QCD input for a QCD-assisted Polyakov loop, loop enhanced Quark-Meson model. That's what we did. So some of the input parameters and some of the dynamics is taken from QCD. And if you are interested in, this is a paper with Weiji Fu, Xiaofeng Lu, Fabian Rennecke, and two PhD students of Weiji in Dalian, and came out a couple of months ago. So yet again, we make a benchmark of this model at zero chemical potential, and we look at fluctuation observables. This is the kurtosis, this is the 6th order cumulant, 8th order cumulant in comparison to lattice results. Right? So forget about the hot QCD results because they have not been continuum extrapolated. So I mean, there's nothing wrong with them. Maybe we should have taken them out here, but I took the plots from the paper in order for you, if you look at the paper, that you recognize what I'm showing you here. But for these cumulants, we are compatible with the Wuppertal-Budapest results for fluctuation observables. Right, and of course you see that the higher we go with the cumulants, the larger the error gets, right? So I mean, for this cumulant to say we are compatible is not saying too much because the error bars from the lattice results are very big.
But your results is red curve, right? It is hard.
Our results is the red curve, exactly, and the lattice.
But it also must have some errors, right, on it. It is shown like a curve, but.
Yeah, no. I mean, now what the lattice shows us is the statistical error.
Yes.
And we don't have.
That is understandable.
Yes, we don't have a statistical error. What we have is a systematic error. Okay, and we don't show it here. I will tell this later when we go to a finite chemical potential. Okay, but our computational error, we don't have a statistical error because we don't have a Monte Carlo method, right? We just compute diagrams. And the computational errors in our computations of the diagrams is so small you won't see it. Okay, you see there's a small band which comes from a determination of the temperatures. But so we don't have a statistical error and the numerical error is pretty small. Okay. So now, of course, uncertainty comes in by the determination of the freeze-out curve. If we now want to compare to fluctuations of conserved charges with the experiment, we have different ways to determine this freeze-out curve. Yet again, I want to be short here also because of the lack of time. We are approaching, in Germany, it's now 7. But you see that our results, so here, the error bars we have here come from the determination of the chemical potential from our freeze-out curves. And you see, of course, it's getting bigger and bigger. And at the very end here for the 8th order cumulant, if you go to small scattering energies or to large chemical potentials, everything goes, okay? That also comes from the fact that our model loses predictive power, not at mu b over t is 4, but rather at mu b over t is 3/2. I will not go into the error analysis of the model at the moment. I'm happy to talk about this. So this is the validity range of our model. We are at the moment upgrading our computation to functional QCD. And just in order to tell you how far we could go already with the mu b over t is 4 estimate of our reliability bound, it's here. Okay, so we hope actually to present results later this year or beginning of next year. But keep in mind, our results at the moment for the model are valid in this area here. Okay, I may maybe skip this. There have been star measurements more recently put out, and our results are fairly compatible with the star measurements. But keep in mind, I mean, we are computing really baryon number fluctuations. That's not really what you measure in star. There is the error of the freeze-out curve. So there are loads of systematic errors and also errors in terms of what are we computing, what is measured in the experiment. Okay, so now the last thing is, if you look at what I'm showing here, this is the kurtosis. Red means it's positive, blue means it's negative. Now what you're seeing is that if you go towards larger chemical potential, you see regions where the kurtosis is changing quickly. Now, this is a model. And as I told you, this is beyond the reliability regime of the model. But nevertheless, the model has a critical endpoint, which is far out here, so where the cursor is. Okay. And you have to believe me when I tell you, it's an RG method. And we know very well when we see criticality or not. And in this regime, I'm showing you there's no critical scaling in this model. Keep in mind, that's not a statement about QCD because that's not in the reliability regime of QCD. It's a model, but in this whole area, this model is not critical. And we see this, that we can prove. Okay, so yet again, it's not a statement about QCD, but in this model, let's entertain this model as an example for QCD. So first of all, as you already see, we see non-monotonicities in our observables. They are not a sign for criticality. They are a sign of what you see here. If you go to larger chemical potentials, the mu dependence of the fluctuation observables becomes wilder. And I grant you, I can tune the model such that the critical endpoint, which is anyway here, goes away and nothing changes with these predictions. So I'm not saying this is QCD. What I'm saying is I couldn't distinguish in this model with the observables I have, which are roughly compatible with the experimental results, whether a critical endpoint is here, or not present at all. So I think we have to be very careful in interpreting signs of non-monotonicities, whether they are there or not, as signs of critical, approaching a critical regime. Here, nothing is critical. Okay, and keep in mind, because I'm always told, I tell that there's no critical scaling and so on in QCD. No, I'm not. I'm just saying I have a model, which here is QCD. Here it's just a model. It has no critical scaling and shows what sometimes is interpreted as a signature of critical scaling. In this model, it's not. And whatever it is, it's a consistent model. It has a critical endpoint. It shows something which you may or may not interpret as signs of critical scaling. And I'm just telling you, here it's not. So one should be careful also in QCD. Okay, last thing concerns the Taylor expansion, which is a very nice tool in order to go from mu is 0 to results towards higher chemical potential. And what I'm showing here are results of our model computation. We are taking our expansion coefficients at 0 chemical potential and compare this to predictions for R42, where you do the same with a lattice, right? And you see we are fairly compatible with the lattice prediction, which is clear because our correlation functions are compatible with the lattice. Now we go to larger chemical potential, and that's what happens. So these wiggly things are the model results. While if you do the Taylor expansion in the model or in QCD, you see a monotonous behavior, whereas the true correlation function, so fluctuation observable of the model, shows this wiggly behavior. Now you could say, well, okay, I mean, the model breaks down, so that's what you're seeing here. No, what you're seeing here is simply, you do this at a fixed temperature that you're scanning through the phase diagram and you're going through this area, and that is causing this wiggling. And that you have this area with positive and negative values for example, for the kurtosis, this is a model independent statement. You will also have this in QCD. Okay, and the only thing I'm saying is this: if you scan through and you're going through these different areas, it will be very difficult to see with the Taylor expansion. Yes, if you up your Taylor expansion, keep in mind, I mean, we went up to 10th order. At some point you may see something, but it will be very difficult to see with lattice computations. It will be in particular very difficult to see with experimental data. I think, I mean, we have to wait a lot for 10th order cumulants or 12th order cumulants or more. So yet again, don't misunderstand me. This is just, if you wish, a game I'm playing with a model. The only thing I'm saying is this non-monotonicity is not a model artifact. It comes from going through these different areas, which will be there. Okay? So which means, so depending on different temperatures, you have different, call it breakdown points for the Taylor expansion. It's not really breakdown points. It just tells that with a limited number of expansion coefficients, you are not capturing the correct behavior. Okay, so you may have to go to 30th order or so to capture this behavior. Okay, so now I'm coming to the end. I hope I have convinced you or convinced you a bit more than before that a functional approach to QCD has its merits. I mean, we are trying to get towards apparent convergence. We are always making our benchmark tests where we have benchmark test results. And I think what is very important and what not that many people appreciate, a self-consistent solution of these functional relations gives us an analytic function in chemical potential. So if we match benchmark results wherever benchmark results exist, it is a QCD consistent extension to larger chemical potential. And it's the only one I know. So I'm happy to hear about others, but I don't know any other. So if you wish, my statement is a functional approach, which is compatible with all the benchmark results which are around, can tell us about larger chemical potentials. Okay, I've shown you our phase structure results, yet again, beware, it's not a prediction of the critical endpoint, it's an estimate. And in this regime, we have to improve our approximation in order to really get a prediction where we can also tell the systematic error is relatively small. I have shown you results for fluctuations of conserved charges, which are for small chemical potentials, mu b over t roughly smaller equal to 3/2. Again, I would say they are reliable, while for larger chemical potentials, they are not. Again, they are estimates, but the qualitative features, they are those of QCD. Okay, that's what I wanted to tell.
Okay, thank you very much for a nice presentation. Now we'll go to questions, and the first question comes from Edward Shrek.
Okay, yeah, I completely with you, Jan, saying that just Taylor expansion and going to the right on this diagram hardly can tell us about what other phases are there. Yes. But you have a model, so why do you go from left to right along the line? What really prevents you from going from the right corner of this diagram, your QCD phase structure, and going down, we know there are something. You already showed that something happened in the diquark channel. Does it
There
lead
are
to the
computa-
superconductor phase? In other words, why you follow this line and don't try to locate other phase diagrams, other phase transitions on that diagram, even crudely? You know, critical point is a subtle feature. Other phases is not subtle feature.
So I have skipped this slide, which is yet again in the slides in the Dropbox. There are computations at so on the right corner of the phase structure. This is a paper, again, a combination of the nuclear structure group in Darmstadt and the FQCD group in Darmstadt, also Schwenk and collaborators and Braun and collaborators, where you have
nuclear meta density.
Yes. Okay. So so we are trying to cover everything, but of course it's a manpower problem. And
Sure.
what I've said about the critical endpoint, that this model we have used for the fluctuations is not trustworthy in this region, is not really true for our QCD approach. So at the moment we are at mu b over t is 4. Of course, we know how to, and we have done this in other occasions in the vacuum, how to put in more channels. The step which really hinders us for essentially, putting out a paper tomorrow is that if you now really go close to the critical endpoint, all estimates tell the critical region will be very small, but nevertheless, in this critical region and a bit around, you need higher order correlations of the order parameters in order to really make a prediction. And that means you need an order parameter potential, which not only has the sigma, so the scalar condensate, it also needs a diquark condensate, and it needs the density condensate. So you have an effective potential of 3 order parameters.
But you are looking for very large qualitative effect, that one of these 3 become very large, right? Like
yes.
You have shown that the pion become very large.
Yes, absolutely. And we can control this, but we have to take this into account. And if you wish, you have, it's not really competing order, but it's getting very close, right? So you need a quantitative approximation there. And we by now have the tools to do this. We can compute potentials of 3, sometimes more order parameters. Okay, and we are building this at the moment into our QCD code, and we are building in the full field spaces. And then I think we will have a prediction.
Yeah, I'm saying, well, you don't need 3 or 5 or how many order. One of them must become large.
Yeah,
but I mean, become dominant. But
yes, I have a good guess which one it is, of course, right? We know what the critical mode is, right? But we don't want to guess. We want to have the potential orders and then see this. Because otherwise, I want to make a prediction with a systematic error I trust. And yes, I can, of course, I could do this tomorrow. I just skip the pion. I just take the sigma, sandwich it a bit with the density mode, because the critical mode is a combination of both, and just give you something tomorrow, right? I want to make a prediction.
But look, so on the left one, you see that in the chiral transition, you see a peak due to it, etc., right? That was, you might say, your prediction. So if you go to...
No, sorry, that's not our prediction. So, I mean, you see the hot QCD results, so that is hot QCD data. So
sure,
it's not...
I don't care in which order it was obtained. So it is their prediction, it is your prediction, it's experimental fact. We know we have some peaks right here. Around 150 MeV, there is a transition. So yes, something like that is expected if you go at large mu and go down in temperature. Something like this is expected with these unknown phases.
Yes. So, we're zooming in to this. So we are also working, if you wish, at small temperatures and large densities, right? So the first thing to get our hands on is the liquid-gas transition. We have a preprint hanging.
This is very difficult.
We have a preprint hanging around there with Kenji and a master student of mine, where we actually get our hands on the nucleon, so the energy gap, so the famous 1617 MeV, and also the density, right? But that at the moment actually is an estimate. I'm very surprised that it works so well, but it's an estimate. So yet again, I mean, that's also why we are looking at the diquarks, because in this regime, what we need is now the baryons come into play. There you need dynamical diquarks as an off-shell mode. And you have to think about the scattering of diquarks and quarks into a baryon. Also there we have checked that for quite some of the correlation functions, the dynamical baryon does not play too much of a role, but the diquark does.
Right, it's supposed to show condensation.
Yes.
If there is a superconductor.
Yes.
So,
okay. So the this color superconducting phase has been actually not in this paper, but I mean there are other papers by Jens Braun and his group where they have looked into this. But look, I mean yes, it's also interesting. I think having a prediction, and I will be very modest here for the point where this, I mean, along the phase structure where it changes, right, from a crossover, chiral crossover to something, maybe inhomogeneous phase, maybe critical endpoint, whatnot. I think this is interesting also for the beam energy scan. And concerning the fluctuation observables, I have this idea that, so we know it's not critical scaling what we are seeing, which in my opinion is good, because the critical endpoint is not a universal observable, it's a non-universal one. And in my opinion, you will get it with putting together the non-universal information we have, and not the universal one. And also here you say we see a peak here. Yet again, so we have a qualitative approximation for this very small pion masses, but we don't see critical scaling. The critical regime we see is extremely small. And we have redone now the computation with better numerical methods. And the scaling regime is very small. However, I think what is interesting also for pheno applications like chiral transport, the regime where chiral expansion works, this is really big. And I think that's the far more interesting information. Where do chiral expansions work? Where can I use chiral models to describe the dynamics? And that's a rather big region. So criticality is a bit a red herring, in my opinion.
Okay. Any other questions from the audience? I don't see any other raised hands. I do have a quick question sort of on my own. You were talking about mostly thermodynamic properties when using this method. Can you access the hadronic spectrum in, let's say, vacuum or at finite temperature? Or what's the obstacle that's stopping you doing that? So
we can access it, and in the last couple of years, we have looked at extensions of this approach to time-like correlation functions or real-time correlation functions. What we now do a lot is the so-called spectral approach, where we use the spectral representations of all correlation functions, put them into these loops, integrate the momenta out, and then we have spectral intervals left. I think that is very promising. So I have left out a few things here with the results we had in 2017, also 2014 for two flavor QCD in this bosonized approach. I told you already that the Yukawa vertices are the pion, or I mean the the meson wave function, beta-salpeter wave functions, you can get your hand on scattering properties of resonances, right? So with this combination of approach, we have a time-like approach with spectral representations, and we have this hadronization, this dynamical hadronization. Yes, we can, but keep in mind, I mean, there's a fully developed bound state, functional bound state approach with beta-salpeter equations, Faddeev equations, four-body equations, and Dyson-Schwinger equations. A big community is working on this, right? And at least some people in this community are really clever. So now catching up against this is an endeavor I don't want to invest in. Right?
Okay.
And keep in mind also, I mean, the lattice results on the resonance spectrum are extremely impressive. Right? So I see, if you wish, an area of interest in really scattering processes. So if you really look at dynamics, of course, you have a problem on the lattice. Right?
Yeah.
And of course, specific resonances is still very difficult to get your hand on, but the progress on hadron resonances on the lattice is well, I think I don't have to tell this here.
Right,
it's great.
right. Sort of related question to that is the transport coefficients. Since you do have correlation functions, quite a few of them, perhaps anyone you want to calculate, you could extract transport coefficients, right?
No, they are Euclidean.
No. We have done this in 2014, 15 for the shear viscosity. So what we did there, I mean, Ed is correct. At that time, it was Euclidean. We have reconstructed the gluon propagator from the data. So yes, reconstruction is an ill-conditioned problem, but we know very well where the ill condition, I mean, hits you hardest. It's the low frequency regime, which is actually the most important for transport coefficient, because you take derivatives at vanishing frequency, the frequency derivatives. So we computed the spectral representations of our correlation functions and put them into a diagrammatic representation for the shear viscosity. And that lowers this uncertainty twice, because the derivative you have, the frequency derivative you have for this representation now hits the distribution function, the thermal distribution function in this loop representation, and you have an integral over frequencies. So the ambiguity you have for the reconstructions at low frequencies is doubly suppressed in comparison to being enhanced if you just take the correlation functions of the energy momentum tensor and do a reconstruction. But I agree, I mean, reconstructions are ill-conditioned. And in particular, if you look at the transport properties, which are the thermal properties, and I mean, I think there also, if you go to the lattice results, which are in position space, you change the temperature, and everything changes. If you go to frequency space, you change your temperature, and the first, or the vanishing and the first non-vanishing Matsubara frequency change, nothing else. And now you want to extract the frequency derivative from 2 points. That's courageous.
Well,
so,
impossible.
But now, we have time-like correlation functions. We're working on gluon correlation functions, on quark spectral functions, and we are computing right now transport coefficients from them. And now we are not, I mean, we are still finishing some work on shear viscosity, because now we can also, which was a bit a problem in 2015, we can, the absolute height of the minimum, we can now get our hands on. Right, and the estimate already there was it's not close to the bound, and so what we are doing now is essentially confirming this suggestion at the time.
Not close means bigger or smaller?
It's bigger.
Bigger, of course.
Okay.
It's far bigger.
Okay, thanks. I see another hand. Electra, go ahead, please.
Thanks for interesting talk, Jan. And you mentioned condensates. And besides the usual condensates, there is an unusual dimension to a sort of condensate, which is coming from Fourier transform of string, if it depends on order of perturbation theory, and its manifestation of string at short dimension distances. And is it possible to have some just counterparts in your approach, say in your full gluonic propagator of this effect?
I mean, this has been a long-standing discussion in the community, whether there are these order 2 condensate or A-squared condensate. And I always stayed a bit away from this.
Yeah.
Not because I think they are not there, but the definition of them in a gauge invariant way is a bit difficult. Right. And how they manifest themselves in a gauge variant way is even more difficult. So if you wish, I mean, that is what people have done. If you look at an operator product expansion and try to match it to the gluon propagator we have, you see an A-squared contribution, right? So that has actually been done, so not by me, for the reasons I have told. But in a way, an operator product expansion will see this. But so more I cannot tell, because in a way for us, it was then not too, if you wish, too interesting, because we have the object. So we have the gluon propagator, and whether we can expand in an operator product expansion for us was not interesting. I'm not saying it's not interesting, but we had no use.
Just a way of matching perturbative and a non-perturbative result, because its appearance depends on the order of perturbation theory. Because you have a full propagator, I was thinking maybe some just counterparts of it can be there.
People have done this, and also recently, I think there's a lattice paper by Rodriguez Quintero and collaborators, where they look into this operator product expansion. Okay, so I mean, if you send me a mail, because I'm now traveling essentially, I can give you the reference.
Okay, thanks.
Yeah. Okay, thank you. I don't see any other raised hands, so I want to use this opportunity to thank Jan for a nice presentation. And with that, we will finish the official part.